Hello, everyone. So far in the course, we've looked at limits and we've looked at differential calculus. And now it's time to start looking at integral calculus, which deals with finding areas and volumes and accumulations. And it will seem for a little bit quite disconnected from what we did with differentiation, but pretty soon we'll have the fundamental theorem of calculus that will basically show that differentiation and integration are two halves of the same coin somehow. So they're connected by this theorem called fundamental theorem of calculus. Okay, but for now, let's get started with looking at integral calculus. And rather than do everything in general, I think it's helpful to have first an example. So in this video, I want to go over an example that has all the key features of integration that we're going to talk about. And then after that, we'll talk about it more in general. So before we do that, let's look at the main question. So the area problem asked, how can we calculate the area of some complicated region? And if it's a rectangle or if it's a triangle or a circle or some kind of node region, then we have these area formulas. But if it's a general region, this maybe just something drawn or something that arises somehow from some application and you want to find the area, we don't really have any easy way to do it. So we should start by an approximation. And maybe you did this thing in high school or in primary school or whatever, where you have some squared paper and you kind of lay your shape over and you count the number of squares, and that gives you an approximation for the area. And the smaller the squares, the more accurate the approximation you get, and this gives you a way to estimate the area. So kind of what we do is based on that, except we need to be a little bit more systematic because we're dealing with functions and we don't know what's happening exactly in calculus. So, okay, so here is the idea. We approximate by rectangles, we add their areas. More rectangles give better approximations. The limit gives the true area. So to go from that step where we're counting rectangles or counting areas, to get the true answer, we have to use limits. And how do we represent these shapes that we're trying to find the area of? Okay, we're doing mathematics, so we need some systematic way to represent these shapes. We're going to represent them with functions, right? So our areas are going to be modeled by areas between a function and an axis. So suppose that f is a non-negative continuous function. Find the area bounded by the curve and the x-axis, and x equals a and x equals b. So here is that shape in a picture. So we have a non-negative function, we have the x-axis, so it's bounded on the left by x equals a, and it's bounded on the right by x equals b. And you might say, this is a pretty special area. A lot of things I might sketch in my pencil can't necessarily be modeled in this way. For instance, one of the sides is a straight line, or actually three of them are straight lines. But okay, if you combine functions and do various tweaks, you can go from these regions to any kind of complicated region you like very, very easily. So for now, we're going to start off with this, but later we'll be looking at areas between curves and more general things. So understanding this kind of fundamental building block is going to help us to go a long way. Okay, so how do we do it? Let's get started with an example. Basically, the idea is going to be everything is going to be as we said, right? We have the area under a graph. We want to approximate systematically by rectangles. We add the areas of the rectangles. That gives us an area for the estimate for the area of the region. And then as we take more rectangles, we get better and better approximations. So let's start with the easiest possible example, which will be y equals x squared. And so the area beneath y equals x squared and above the x-axis from x equals 0 to x equals 1. So that's when our function is y equals x squared. Notice I said that y equals x was the easiest, y equals x squared was the easiest because, going back to the picture, if I had y equals constant, it would just be a rectangle. And if we had y equals x, it would just be a triangle or a rhomboid or something like that. It would be some kind of known shape. So the easiest one that we don't have a known formula for is going to be y equals x squared. So let's use 4 right rectangles to approximate the area under the graph. So it's going to be clear what I mean in a second by right rectangles. So here is our function y equals x squared. And we want to approximate by 4 right rectangles. So here is the approximation that I drew. So how did we get this? Again, we have the same graph y equals x squared, but then we decided to approximate by these 4 rectangles. So how did we get these 4 rectangles? So firstly, we divide the base 0, 1. So by the way, to specify a rectangle, we need two things, right? We need to know what is the base and we need to know what is the height. So we need to figure out the base and the height. And since we're using right rectangles, since we're using 4 rectangles, we want to approximate by 4. So we should chop 0, 1 up into 4 pieces. So we start off by dividing 0, 1 into 4 pieces because we're going to want 4 rectangles. So we divide 0, 1 into 4 subintervals, and since 0, 1 has length 1, each of those subintervals is going to have length 1 over 4. Okay, and if we're splitting evenly, which we always make sure we do, we can see what those subintervals are going to be, right? If we divide 0, 1 into 4 subintervals, we're going to go from 0 to 1/4, from 1/4 to 1/2, from 1/2 to 3/4, and 3/4 to 1. So these are then the bases of our rectangles. And then next we need to specify what are the heights of the different rectangles. And since we're using right rectangles, on each subinterval, we make the height of the rectangle the value of our function at the right endpoint. See here, for instance, on 0 to 1/4, the value of the function at the right endpoint is 1/4 squared. Remember, the function is x squared. So the height of this rectangle is 1/4 squared. For 1/4 to 1/2, we use the value of the function at the right endpoint, which is a half. Plug that into the function, we get a half squared. For a half to 3/4, the right endpoint is 3/4. We evaluate the function at 3/4. 3/4 squared is the height of our rectangle. And then lastly, from 3/4 to 1, we use the value of the function at the right endpoint, so we'd use 1 squared. That's the height of our rectangle. Okay, so now we managed to specify both the base of the rectangles and the height of the rectangle. Okay, so now we managed to specify the heights. Okay, so now to find an estimate of the area using 4 right rectangles, we just add up the heights or add up the areas of these rectangles. So for each rectangle, we know how to calculate areas of rectangles. It's just base times height. So we go ahead and do that. So we add the sums of the rectangles. R4 stands for the approximation we get if we use 4 right rectangles. So the area of the first one rather will be base times height. It will be 1/4 times 1/4 squared. The area of the second one will be base times height. It will be 1/4 times a half squared. The area of the next one, it will be 1/4 times 3/4 squared. Then finally 1/4 times 1 squared. Okay, so each of these 4 terms is the area of one of these rectangles. Okay, if you plug those into a calculator and you add them up, you'll get 0.46875. So this was the estimate of the area under y equals x squared from 0 to 1 using 4 right rectangles. And just to say again, the steps were we divide 0, 1 up into 4 equal subintervals. Those are the bases of our rectangles. And since we're using right rectangles, for each subinterval, we place a rectangle over that, and the height of the rectangle is the value of our function at the right endpoint. And this has all the main characteristics of what we're doing. So in a second, we'll talk about left rectangles, but it's pretty much the same. Better estimates, we're going to use more rectangles. So rather than dividing by 4, we divide into 8 or 16 or however many. We could have different functions. We could have different endpoints of our intervals, but everything is pretty much summarized in this key example, right? We divide systematically our interval up into smaller subintervals, depending on how many rectangles we're using. That does give us the base of our rectangles, and then the height of the rectangle will come from whether we're using right endpoints or left endpoints or something else. Okay, so by the way, these rectangles in the picture, clearly the rectangles that we're using to approximate the area lie above the curve. So the area under the rectangles, or the area of the rectangles, is bigger than the area under the curve. So this is going to be an overestimate, right? Because our estimate was the area of the rectangles. That's more than the area under the curve, just because the area under the curve is enclosed by the rectangles. So this is an overestimate. Let's compare with left rectangles. So suppose instead of using 4 right rectangles, we use 4 left rectangles. What kind of picture would we get? So we would play the same game, right? We have the same function x squared from 0 to 1. We chop 0, 1 up into 4 pieces. Each of them are length 1/4. So our subintervals are the same again, right? 0 to 1/4 to 1/2 to 3/4 to 1. But now instead, on each subinterval, we use the value of our function at the left endpoint. So for instance, from 0 to 1/4, the left endpoint is 0. So the height of the rectangle is 0 squared. Okay, it's kind of a weird rectangle, but okay, it's a degenerate rectangle. The height is 0 squared. From 1/4 to 1/2, we use the value at the right endpoint, so 1/4 squared. From 1/2 to 3/4, we use the value at the left endpoint, so 1/2 squared. And from 3/4 to 1, we use the value at the left endpoint, so we get 3/4 squared. So notice everything was kind of shifted if we compare to the previous example. So in the previous example, on the first one, it was 1/4 squared, then it was 1/2 squared, then it was 3/4 squared, then it was 1 squared. So this one features an extra height. It features this height 0 squared, but it loses the rectangle that had height 1 squared. So with these ones, we include the value at the left endpoint, but with the right endpoint, we include the value at the right endpoint. So notice we don't use all the y values in both of them. We either use all the ones aligned to the left or all the ones aligned to the right. Okay, so if we add up the areas of these rectangles, right, we play the same game. We do base times height on each one. The first one is 1/4 times 0 squared. The second one, the base is 1/4. The height is 1/4 squared, and so on and so on. We get this slightly different sum, which comes out to 0.21875. And now, since the rectangles lie below the curve, clearly the areas of the rectangles is smaller than the area under the curve, so this is going to be an underestimate. Okay, so if the rectangles are under the curve, we get an underestimate. If the rectangles are above the curve, we get an overestimate. And by the way, it's not always the case. So here we had the right rectangles give an overestimate, left rectangles give an underestimate. It's not always the case that left rectangles underestimate. It just depends on which way the function is going. So here the function is going up. It's an increasing function. If you had a decreasing function, the situation would be reversed. If you had a decreasing function, the left rectangles would give you an overestimate instead. So do be careful, think what the picture would look like, think if your function's going up or down, if they ever ask you for an estimate, or whether it's an overestimate or an underestimate. And we might say, okay, if we compare the numbers we got, R4 was 0.4 something, our L4 was 0.2 something. There's quite a big gap between those two. And if you've done calculus before, you would probably think the answer is 1/3. It's okay if you haven't. So how do we close that gap? Well, as we talked about, the solution is to use more and more rectangles. So sorry for the crude picture, but here's what you get, for instance, if you had 8 rectangles, right? We would chop 0, 1 up into 8 pieces. So here we have 1, 2, 3, 4, 5, 6, 7, 8 rectangles. And then let's say we want to use right rectangles. On each of those rectangles, we would use the value of the function at the right endpoint. And clearly, these give a much better approximation to the area than if we only used 4 rectangles. So the more rectangles we use, the better the approximation for the area that we get. Okay, so they could ask you, or we could ask you, compute the approximation with some number of rectangles, with 3 rectangles, 4, 5. Probably 8 would be a bit of a pain to do, but you could do it. Okay, so now how do we get the true area? So to get the true area, we have to take more and more rectangles and let the number of rectangles go to infinity. So the more rectangles we have, the better the approximation we get. If we let that go to infinity, we're going to get, in the end, the true area. We get closer and closer, and in the limit, we get the true area. So let's suppose that Rn is the approximation we get if we use n right rectangles, where n is some whole number that we don't know right now. It could be, stands for different things. So we want to compute Rn, and then we want to show that the limit as n goes to infinity of Rn equals 1/3. So let's try to do that. So let's remember the strategy we had. So if we divided, if we had 4 right rectangles, we were dividing 0, 1 into 4 pieces. Now we have n rectangles, so we are dividing 0, 1 into n pieces. And the length of 0, 1 is 1. So each piece is going to have length 1/n, right? If we divide it into 4 pieces, they had length 1/4. If we divide into 8 pieces, they have length 1/8. Here we're dividing into n pieces, so they have length 1/n. Okay, so here are the subintervals, right? Each time we go along by 1/n. So we have 0 to 1/n to 2/n to 3/n and so on until the last one is n minus 1/n to 1. So these are our subintervals that form the base of our rectangles. Now we need to specify the height of our rectangles. And since we're using n right rectangles, for each rectangle, the height should be the value of the function at the right endpoint. So for instance, on 0 to 1/n, the right endpoint is 1/n. So over that, the height should be the value of y equals x squared at 1/n. So we should have a height 1/n squared. For 1/n to 2/n, the right endpoint is 2/n. So we should use the value of the function at 2/n. We are going to get 2/n squared. Okay, and so on. So if 2/n to 3/n, the right endpoint is 3/n. We use the value of our function at 3/n, 3/n squared. Until we get to the end, okay, there are lots in the middle that we're not writing because we don't know, we don't know how large n is. We can't write them all. Then lastly, we have 1 is the right endpoint of the last interval, so we are going to do 1 squared. So now we have everything we need, right? We know the base of our rectangles, or we know the length of the base. It's always 1/n, and we know the heights of the rectangles. So we can just add up the areas. Okay, so the first rectangle is going to be of width 1/n, height 1/n squared. We multiply those together. We get 1/n times 1/n squared. The second rectangle is of base 1/n, right? All the bases have the same length. The base is 1/n, the height is 2/n squared. The third, the base is 1/n, the height is 3/n squared. We multiply them together and so on until we get to the last one. The last one, the base has length 1/n and height 1 squared. So we add that final area. So if now we have to try to simplify this and see what happens in the limit, right? We managed to compute Rn. Okay, so how can we simplify this? Okay, we see that every term has a 1/n, and then every term is also divided by n squared, right? Here we square the top and bottom, we get 1 squared over n squared, 2 squared over n squared, 3 squared over n squared, and so on. So we can factorize out of the bottom an n cubed. So you can trust me, if you do a little bit of algebra, you can rewrite this as 1/n cubed. And then we have the top, so 1 squared plus 2 squared plus 3 squared up to n squared. So we managed to come up with a formula for Rn. Now we need to somehow find the limit. Okay, well, we can't find the limit of this because we don't know how many, we're adding n terms. So we want some way to first simplify 1 squared plus 2 squared plus 3 squared up to n squared. And okay, if you don't know that formula, there is a formula which I'm gonna quote, which you can prove with induction if you care to look that up, but don't worry, that's not on the syllabus. You can just assume this formula or write this, or remember this formula, write it down somewhere. So the sum of the first n squares is n times n plus 1 times 2n plus 1 divided by 6. So you could check this, the sum of the first 3 squares would be, we plug in n equals 3, the sum of the first 4 squares would be plug in n equals 4, whatever. But okay, now we can just replace that complicated sum that we had by this shorter formula. So by n times n plus 1 times 2n plus 1. Okay, so here we did exactly that. We replaced this complicated beast with the simpler formula. And now we want to try to find the limit of this because the second part of the question asks us to find the limit of Rn. So we want to look at the limit. So on the top, what do we have? We have, if we were to multiply out all the terms, which I don't want to do right now, but which you could, is that we have a polynomial of degree 3, right? If we multiplied out all the terms, we would get 2n cubed, and then we had some other stuff, it would be a polynomial of degree 3. On the bottom, we have n cubed, which is also of degree 3. So we are hopefully looking for a limit. So let's simplify. So we have n on the top and we have n cubed on the bottom. So straight away we can cancel one of the n's. And then we're left with divide by n squared. We could rewrite this as n plus 1 divided by n, 2n plus 1 divided by n, and then of course there is a 1 over 6. So we, instead of dividing everything by n squared, we divide each of these terms by n. Okay, and then we take the limit of each piece. So we have the 1 over 6, and then the second piece we could simplify as 1 plus 1 over n. 1 over n goes to 0, this is going to go to 1. And then the next piece, this could simplify as 2 plus 1 over n. This is going to go to 2. So this, in the end, this is going to go to 1 over 6 times 1 times 2. So 2 over 6, which is 1/3. Okay, so we successfully calculated first Rn in terms of n. Right, Rn was the approximation we get if we approximate by n right rectangles. And then we looked at what happens as we take more and more rectangles, and we said as the number of rectangles tends to infinity, we get 1/3. And actually, this is the true area. Okay, so this was the informative example that I wanted to go through that will inspire everything we do. So just to summarize, how do we get the area? For instance, we can use n right rectangles. We approximate the region under the graph by n rectangles. So we divide our interval into n equal pieces. Those are the base of our rectangles. The height of our rectangles are the value of the function at the right endpoint. We sum up base times height for each rectangle. That gives us an approximation. The more rectangles we take, the better the estimate we get. If we let the number of rectangles go to infinity, we get the true area. And okay, next time we're going to do this in general with a general function, but everything is going to be the same, just replacing y equals x squared by f of x, replacing 0 by a, 1 by b, and so on and so on. Okay, thanks everyone. See you next time.